Hey everybody, this is Mrs. Johnson. This is MAT 221 Calculus 1. This is section 2.3, which is a topic of how to calculate limits using the limit laws. So here I want to go through the different properties that you need to know to manipulate these limits, this idea of a targeting value of a function. So let's go through these properties that you need to know. We have to assume that all the limits on the right hand or the right-handed limits will exist and that b and k are considered constants. Actually, c is also a constant in these rules also. So rule number one, or law number one, it says that if you take the limit as x approaches c of some number b times a function, in other words, if b is like a vertical stretcher of a function, the number out front, in front of a function, then you can take that number b, whatever that number happens to be, and bring it outside the limit and multiply by the value of the limit. So the limit as x approaches c of some number b times a function is equivalent to that number b multiplied by the limit of the function. Property number two is pretty again, intuitive here. It says the limit as x approaches c of the sum or difference of two functions. So if you have a function added to a function or a function subtracted from a function, then this limit is equivalent to the limit of the first function plus or minus the limit of the second function. Or in words, we could say this as the limit of a sum or difference is equal to the sum or difference of the limits. Rule number three says that if you have the limit of the product of two functions, that is equivalent to the limit of the first function multiplied by the limit of the second function. In other words, the limit of a product of two functions is equal to the limit of each function multiplied together. So the limit of a product is equal to the product of the limits. Rule number four, again, this is intuitive. It says if I take the limit of the difference, division of two functions or the quotient of two functions, then that limit is equal to the limit of the numerator function applied as x approaches c divided by the limit of the lower function or the denominator function applied as x approaches c, so long as the denominator is not equal to 0. Because we know that a 0 denominator is undefined in the real number system. So this one says that the limit of a quotient of two functions is equal to the quotient of the limits. So again, pretty intuitive, all of these rules, and you'll see how we use them as we move forward. Rule number five is, again, kind of intuitive if you think of k as some constant. So if you said, if I'm taking the limit as x approaches some number c of a constant function, and remember a constant function is just a horizontal line, that means anywhere on that function, no matter what x value I pick, the output of the function is always going to be that number k. So that means the limit will always equal k. And then the last one we're going to look at for these six anyway, says the limit of a linear function y equals x as x approaches c is equal to c. This one, again, intuitively, if we think about this, the equation y equals x, so for every x value, the y value is going to match it. So here, the limit of a function y equals x is simply going to equal that c value. Let me take these limit properties and show you how we would use them graphically. So in the last section, in section 2.2, we talked about a limit being a targeting value. So I want to use these limit laws and the figures below to see if we can come up with the answers to these three problems here. What about if I said I wanted to know the limit as x approaches -2 of f of x plus 5 times g of x? Well, what I would do here is first say, well, let's use our properties. The limit of the addition of two functions is equal to the limit of the first function plus the limit of the second function. But the second function also has a number in front of it, which is rule number one. If I have a number multiplied by a function, I can take that number and bring it to the front. So part A is equivalent to the limit as x approaches -2 of f of x plus 5 times the limit as x approaches -2 of g of x. So I have applied two of the rules here. I've used actually rules 1 and 2. Now that I've done that, let's look at the function and actually find these values. So what is the limit as x approaches -2? So if this is 1, here's 0, here's -1, here's -2. The red function is f of x, so let's look. As x approaches -2 on the f function, there is a targeting value. That targeting value is 1. Even though we have this dot up there, it's trying to confuse us. It has nothing to do with the targeting value as x approaches -2 on the f function would equal 1. Now let's look at the g function. At x equals -2, the targeting value of the g function from the left and from the right, the output value is targeting -1. All right, so let's put those values in here. So we get this first value would be 1. The second value would be -1, but I'm going to multiply that by 5. And when I do the math here, I get 1 minus 5, which is -4. So the answer to number 1, part A, is -4. Let's look at the second function, or the second example. I want the limit of this product of two functions, and using rule number 3, we know that the limit of a product is equal to the product of the limits, so we would take the first limit and multiply it by the second limit. Now let's go to the graph and look at what these limits are. Well, the limit of the f function as x approaches 1 looks to be an output of 2. Okay. The limit as x approaches the g function as x approaches 1, well, the left-handed limit is targeting -2. The right-handed limit is targeting -1. We know if our targets are two different values, then the limit does not exist. Therefore, we get 2 times something that does not exist. So in other words, we can't find this limit because the second part of the limit does not exist. Let's look at part C. Part C says same two functions. Now we're looking at as x approaches 2. So the f function as x approaches 2 from the right, from the left, as x approaches 2 from the right. On the f function, I have a targeting value of about 1.5-ish. On the g function, let's see, as x approaches 2 from the left, I have a targeting value of 0. When x approaches 2 from the right, I have a targeting value of 0. So when I put this in here, I know that the limit of a quotient is equal to the quotient of the limits. But when I put in my limits, I get a 0 down here. And when that happens, I have now an undefined thing in the real number system. So I cannot be found. It does not exist because I cannot find that this is an undefined value in mathematics. All right. Let's add some more to these power laws, these limit laws. Number 7 rule for limits is saying that if I take the limit of a function raised to a power, it is the same thing as taking the limit of the whole function raised to that same power, where n is a positive number. We also have, if I take the limit of x raised to some power, I can actually just, this is a power function, I could just do a substitution and substitute a right in here, and this is going to equal a to the n, where a is a positive, n is a positive number. Here's another, the limit as x approaches a of a root function of x. I can just do a substitution and substitute a in for x and get that is equal to this, which is actually bringing us to a bigger property, and that one is this. This is bringing us to what's called the direct substitution property. It says that if f is a polynomial or a rational function and a is in the domain of the function, then the value of the limit is simply equal to the value of the function at that point. In other words, if I have a function where I have a polynomial or a rational function where I have it, this number is in the domain, then I can just do a substitution right into the function and it will give me what the value of the limit is, because the value of the limit and the value of the function will be equal to each other. This is called the direct substitution property. Functions that with the direct substitution property are called continuous at a. In other words, there's no holes or jumps or anything at that value of a. In general, we have this as our useful fact here, that if f and g are both equal to each other, when x is not equal to a, then the value of the limit of the f function and the value of the limit of the g function will equal each other, provided the limit exists. So this is called the direct substitution property. This is going to be used often if I have a polynomial or rational function, as long as that number that I'm approaching is in the domain. So let me give you a couple of examples. So the easiest way to find a limit is to use substitution if I have a rational or a polynomial function. Now this is a rational function. The second one is a rational function. But the third one is actually a trigonometric function, so we have to worry about that one when we get to it. Let's do each example. Let's see if I can do it by direct substitution. If I put in 1 in for x, I would get the limit as x approaches 1 is equal to 1 over 1 plus 1, which equals 1/2. So in this case, x equals 1 is in the domain, so I can do just a direct substitution, and I get the limit of this function is simply equal to 1/2. The value of the function is equal to the value of the limit. Let's put a 0 in here. Let's see what happens. If I put in 0 in here, direct substitution, when I'm putting in 0, I get 0 minus 3 over 0 squared minus 1, which equals -3 over -1, which equals 3. Again, 0 is in the domain, so I can do a direct substitution, and I get a limit. Now, mind you, if I had said at x equals 1, this would not be in the domain. Or in this case, if I said x equals -1, that would not be in the domain of this function, so I couldn't do a direct substitution. I'd have to do that some other way. Let's put in pi, do a direct substitution. Do you know your cosine? Do you know your cosine of pi? What is cosine of pi? Do you remember these trig functions? Cosine of pi is equal to -1. When I do this, a substitution, I get -1 over 3. That is in the domain, so I get, there we go. These are the easiest way to find a limit of a function if I can do it this way. Some limits are best calculated by first finding the left-hand and right-hand limits, and then following the theorem that is below that says that two-sided limit exists only if the one-sided limits exist and are equal to each other. So remember, the value of the limit is equal to some number L if and only if the left-handed limit and the right-handed limit are both equal to that same number L. Let's remember that the limit is only existing if I can approach from both sides and still equal each other. Now, these particular theorems that we have are additional properties for limits, but we're going to skip them for this semester. These are theorems using what's called the squeeze theorem, which we definitely will use in Calculus 2. But I'm going to skip them here in Calc 1 because they're optional properties and optional topics for Calc 1. So I'll stop our video here. This is some of the things that we wanted to talk about for section 2.3, talking about the evaluation of limits.